Hi, in this video, we want to take a look at support vector machines. All right, so support vector machines, the big idea is that what we're going to do, I'm going to describe the long way. We're not going to do the long way. We're going to do the shortcut, but follow my idea. What we're going to do is we're going to take our data. I've got numeric predictor variables, and I've got classification problem. I'm going to take my multidimensional data. I'm going to map it to a higher dimension. Now, why am I going to map it to a higher dimension? That's a very good question. Glad you asked. In that higher dimension situation, it's easier to partition those classification values. So let's say I'm working on a project where I want to build a model that predicts whether a mushroom is edible or poisonous. I'm going to be using the Kaggle data set for this. And so in the regular multidimensional data that I have with my predictor variables, it's not real clear how I can cut it using a hyperplane. We're invoking some mathematical geometry. But if I take it to a higher dimension, it's easy peasy lemon squeezy. All right, so what we're going to do is I'm going to take my original data, send it up to a higher dimension. I'm going to figure out hyperplanes that will partition the higher dimensional space. And then I'm going to take the partitioned method and map that back down to the original dimensions of what I've got, and then classify what's going on, classify each of the points by which partition a data point lands in. All right, so now here's the cool thing. Here's the mathematically the most interesting aspect of support vector machines is that using dot products and the kernel, in fact, I don't have to go through this whole process. I can just skip straight to the end. So computationally, this is a lot faster. Mathematically, the geometry of this is really, really cool. So I've got like really, really slick, higher dimensional geometry going on. We got higher hyperplanes happening. But then to top it off, that cherry on top, the kernel using with the dot product sets it up so mathematically I'm shortcutting this, and computationally this is quick and fast. All right, so support vector machines are a powerful class of supervised learning algorithms for classification and regression. I'm only going to present classification here. That's how it was presented to me, how I see it most often. We can use it for regression. I do need to say a personal disclaimer. I've never had support vector machines be my top model on real data. It does a really good job on the data set I'm about to show, but at work, when I've had projects with real data, I've never had support vector machines come out on top, but they definitely have the potential. So the aim with support vector machines is to find the best hyperplane like cuts that divide the data set into subsets, and each subset gets like labeled by a classification level. Now, this is really useful when we can't find like an easy cut with our original data with the original dimension of the data. And so from a math point of view, this is very, very beautiful. This is invoking some really cool geometry aspects, higher dimensional geometry. And so I find this exciting for that purpose. And so we're going to create a set of hyperplanes that cuts that higher dimension space into subsets, and then it'll be a partition, and then we're going to map it back to the regular space that we have, and that's how we're going to work it out. Now, when I do my cuts, something that's going to be important is this idea of a margin. All right, so imagine I've got a dot here, a dot here. All right. And one thing I could do for my cut, I could come in at an angle where it comes in like just a little bit below this dot and just a little bit above this dot. And you would see that, yeah, that will partition, the higher dimensional space, but this dot is really close to the boundary. This dot is really close to the boundary. What we're going to do with our margin, we're going to try to find the cut that maximizes the distance between the points and the hyperplane. So we would be going straight down the middle. So like the line, broken up by my nose would be where I would want my hyperplane because I want maximum distance between the point and the hyperplane. All right, so I'm going to set up my workspace for the examples. I'm going to suppress the number of digits to just 2. I'm going to try to avoid scientific notation. Don't bark at me for warnings I already know about. Make sure that there's no artifacts floating around in my workspace. And then here, I'm going to use piping from the tidyverse. So I'm using the Magritter package. All right, so the margin is the distance between the separating hyperplane and the nearest point of data for either class. All right, so we want to make that as large as possible. A support vector machine aims to maximize this margin, ensuring the most robust and generalizability that we could possibly get for our classification schema. So here, if I take the dot product and add, here we want equal to 0, the distance of a point x to the x of I to this hyperplane is going to be this value here, and here we're going to be dividing by our hyperplane, or the vector that defines our hyperplane. So I'm taking the row vector of the observation, dot product with the hyperplane's defining vector, then add the constant. And here we take, we're dividing by the norm of the hyperplane. The norm aspect is not as important. We just need to be consistent about the norm of our hyperplanes when we have multiple. Now, the next thing we need to talk about is hard versus soft margin. Hard margin says we have to have 100% pure classifications within my training set when I start chopping up the higher dimensional space with hyperplanes. And so in this situation, when we go through and we do our hyperplanes and we chop our space into subsets, my hard margin requirement is that every single partition has to have the same classification every single time throughout. Now, depending, with larger sets of data, this is probably going to be pretty hard unless I have a pretty simple situation. And so what will happen here if I have a hard margin is that the support vector machine process is going to keep on chopping with more and more hyperplanes and really overfitting more than likely to make sure that we get that absolute 100% correct by the training data model. But I don't want 100% on the training data. I want as accurate as possible on the test data. Now, the soft margin is where we allow some misclassification to make sure that we don't overfit and we want a generalizable model. And so basically what this does for us is that we prevent the system from creating hyperplanes that we don't need to have. All right, so I'm going to use the mushrooms data set from Kaggle. I'm loading my data. Now, if you remember from a previous video, I went through and I did binary binning on all of the categorical data. So all of my predictor variables are 2-level binary variables. And I made the goal of putting in the binary groups so that ones with a larger percentage of poisonous are in one group, ones with a larger percentage of edible are in a different group. And that is how I worked it out, tried to get 50-50. All right, and so then this data set does not come with an assigned train test split, so I went ahead and just built that myself. Now the kernel trick here, what this is doing is that this is preventing us from actually having to manually send our data to higher dimensions, do the hyperplanes, send it back to the original dimensions. The kernel trick is that we're shortcutting it and we're just getting the result using the dot product. And so this is computationally far more efficient than what we would have. And so and this is important for non-linearly separable data. If it's linearly separable, I don't actually need to go into a higher dimension. I can just take the original dimension and slice with a hyperplane. But most situations, it's not going to work out. And so we've got several kernels. And probably the three most common are the linear one, then the polynomial, and then the radial basis function, also called Gaussian. And I'll show you how to invoke these using kernlab and R. All right, so what is a support vector machine kernel? So the kernel is a function that computes the dot product between two vectors in a transformed space. Instead of explicitly transforming the vectors into the higher dimension space and then calculating the dot product, the kernel provides a shortcut by directly computing the dot product in the original space. And so this is that really cool trick that I get the results of doing all the hard work of mapping to a higher dimension without actually mapping to a higher dimension. I get my cake without having to bake it. I just get it for free. And so this is computationally very efficient. And so we can create nonlinear decision boundaries without actually having to go through the step of mapping it upward and doing that transformation. So in their basic form, we're going to construct linear hyperplanes to separate our data. So in this situation, the hyperplane is trying to find a linear cut to classify our data. We map to the higher dimension because in the original dimension, there isn't possible to cut the way we want to. But the kernel trick enables us just to shortcut all that work. We get the advantage of sending it and slicing it without having to do the work. And so here, let's run through some examples. So I'm going to show this two different ways. I'm going to show you how to do this in the caret package, which invokes the kernlab package. And then I'm going to show you how to do it in the kernlab package directly. That way, whatever project you're working on, it'll be pretty, you can do whatever's needed. And so with the train function in the caret package, we provide our predictor variable data frame. We provide a vector of our target variable, and then we specify the model that we want. And so in this situation, I'm just saying find the best hyperplane cuts without doing any weird things with our data, without doing any dot products. Just do the best that you can. And we can see right out of the gate, I get a 0.98 accuracy. Not too shabby. Now here, if I want to use kernlab directly, I need the k svm function to evoke this. Now, something about this that's important is that the kernlab package doesn't really like data frames. It wants matrices. I had trouble with this. When I sat down to make this video, I had forgotten that. I couldn't figure out the error for a bit, but I got it. So it wants the predictor variables, which have to be all numeric, to be in the form of a matrix. And here, our target variable, you'll notice that here I actually have it as a data frame, and it says it is a factor in a data frame. And so, we can see, the results that we've got. Now, the polynomial kernel, this of the three that I worked on took by far the longest to compute, by the way. But you notice that everything's the same way as I had it before, and I've got the x here, I've got the y, and I'm saying svm poly, and you'll notice that it went through different scale values and different c values, and so it's just running through different parameters. And you can see that we did like pretty good accuracy, and this is the bootstrap accuracy, not just regular straight training accuracy. And so here is the best performing scale in C. C connects to the margin. Now, when I run KSVM for the polynomial support vector machine, I need to, in a list, I need to specify the parameters that I want. So up here, you'll notice that I have, degree, scale, and C. Here I've got degree, scale, and C. Offset on this one is on the default value. I had to look up in the help documentation what the offset value. Different kernels have different named parameters in their list. And so now we can see how the model performs. Now for the radial basis function or the Gaussian kernel, all I do is put SVM radial into the training function, and it works it out. And so we can see sigma of 0.15 and C of 0.25. Notice that sigma is not a parameter of the polynomial kernel. All right, so we're going to be having different parameters for different kernels. And there's a whole bunch of different ones that we can also run. And so here is using the kernel lab directly. Notice that here I copied and pasted the best value that there was from the train function. And I get my results. Now, there are other kernels that we can work with. I'm not going to go into depth or even what their parameters are. I just ran these just so that you can see that you have other options. So we have the hyperbolic tangent kernel, hyperbolic tangent dot. We have Laplacian kernel, Laplace dot. We have Bessel kernel. Recognize Bessel from Fourier analysis, by the way. So Bessel dot. ANOVA dots, or the ANOVA radial basis function kernel. Spline dots, or the spline kernel. And so this is a very efficient, very fast model structure to fit, so it's very nice. But something that we need to consider is our choice of kernel. This will have a pretty big impact on the performance of our model. And so if I'm training 1,000 rows of data with 5 columns, each row is the observation. Each column represents a feature or dimension of that observation. When you compute the dot product between two vectors of the data set, you're taking the dot product between two 5-dimensional vectors. And so that's something about this. So we're talking about a lot of dot products. Well, if I have a 1,000 by 5 matrix that I'm doing dot products on, are the vectors length 5 or are they length 1,000? Well, they're length 5. We're doing by rows. So each individual observation is being treated as a vector for the purpose of that dot product. And so the support vectors find the optimal hyperplanes that maximize the margin between two classes. The data points that lie closest to the hyperplane and influence its orientation and position are called the support vectors. Only these support vectors are critical in defining the hyperplanes and making future classifications. So once I figure out what the hyperplanes are, boom, I've got them. I don't worry about anything else in terms of like what my full data set was. The model is basically a collection of hyperplanes, and given which side of the hyperplane a dot is on, what do we label it as? Now, for data prep, a disadvantage of support vector machines is that how we do our data prep will have a huge impact on this. And so, first and foremost, we have to make sure that our data is scaled correctly. That's critically important for support vector machines. Also, it's critically important that we handle outliers. And so there's two major ways to handle the scale. First one is z-score normalization. And I meant to call this rescaling. That's it. But here, when we subtract the min, divide by max minus min, this maps our predictor variables to 0 from 0 to 1, and this is a good choice. I personally prefer z-score normalization, especially imagine if I have an extreme outlier for the max or extreme outlier for the min. I don't like this one as much. I prefer the normalization where I subtract off the sample mean divided by the standard deviation. Outliers can pull things off pretty far. Now, anomalies where it's multidimensional outliers aren't as big of a deal. Outliers here we're more worried about like extreme univariate outliers on this one. Now, our data transformations, we can, yeah, Boxcox, log transformation is a good choice for the situation, but we have to make sure that, when I do my actual scoring of my data, I do the same transformation down the road. Support vector machines cannot handle categorical data. So that we have to recode our data to numeric in some way, shape, or form. We could do categorical smoothing, or we could do dummy variables, whichever one you prefer. Now, we also have to worry about class imbalance since this is a classification problem, and also feature selection. It's important to make sure I don't have junk features or redundant features in my predictor variables. So I want to go and get rid of irrelevant ones. I want to get rid of redundancies through this. For the code that I'm showing you here, I did recursive feature elimination. I started with a full data set, removed one, removed one, until I got a collection of predictors I felt good about. And we want to make sure that we don't have issues with multicollinearity. Basically, if I had multicollinearity, it would make things like hypersensitive to fluctuations in the data. Now, something we need to worry about is binary or multinomial classifications. If it's binary, we just set up our hyperplanes one side or the other, and it's good. It gets more complicated when we have multinomial classification. So for multi-class classification, one thing that we could do is let's say I've got 3 different levels. Well, I could say, like, let's say A versus BC, B versus AC, C versus AB. And so then, I've got, 3 different models for this. Or we could do, A against B, A against C, B against C. Now, there's advantages and disadvantages both ways. We have to figure out how we want to handle this when we're using support vector machines. Now, we can get a confidence score out of the package, and we just put it in. I didn't really feel like going into that any deeper because our focus is on predictions. I want the best prediction possible. Inference really is not as important on this one, because if we're talking about higher dimensions, like, how do I pull inference off of higher dimension data? And so here I want to go through and just compare the results of what we've got. So here, class is the correct true value of what's happening, while over here, this is our different models, the predicted values, test and train. And I see that I've got a mixture of dots here and here. That I'm using the jitter function to kind of wiggle it, but you can see that there's some impurity in these groups that are getting covered up by the different dots. And you can see that, in the predictions, it's like we've got solid groups, even though we don't have solid in the actual original data. Now, also, we want to take a look at our confusion matrix when we do this. And so here is, I'm going to look at test set first. Here is for the linear. And we can see that we had 59 errors, and every single time we predicted edible when it was poisonous. Huh. Now for our training set for the linear, we had 61 errors. Once again, we're saying it's edible when it's not. For test set for polynomial, we say 59 times it's edible when it's poisonous. 61 times when it was poisonous, we said it was edible. This is for the polynomial on the train set. And then on our radial, so we're pretty consistent on this. So for this particular data set, I would use the linear the linear kernel as simple as possible. Not a lot of work, not a lot of time to fit, and I actually have a potential of figuring out some inference off of it since I'm not mapping to a higher dimension. All right, so support vector machines are a very powerful way. They're very sexy in the math community because of the geometry connection. So mathematicians, if you have a stronger math background, you're probably going to like support vector machines because you're invoking some higher dimension geometry. Now, my personal experience is that it's never come out on top for any model I've built, but that's not to say it's not, potentially, a contender. All right, that's all I've got for you. Life is short. Do math.